It's like a ceremony when you close the door. Something's going to happen.
It's quiet.
Good afternoon. How are you? My name is Christian Wells. I'm a professor of anthropology. For those of you who don't know me, don't worry. I work with engineers. So I've heard of some of this stuff before. I'm serving as the external chair for defense to make sure that Kevin's taken care of.
Thank you.
And so the way this will proceed is that Kevin is going to give an overview of his research. And then we're going to open up for questions from the audience. We'll take a short break, see if anyone wants to leave or get more food or whatever, or stick around, and then we'll have questions focused from the committee members. Then the committee will have a few minutes to talk about the proceedings and how things went, and then we will hopefully celebrate with a bunch of champagne. So I would like to call up Kevin's major advisor, the dissertation advisor, Dr. Cunningham. He's going to introduce Kevin.
Co-major advisor. Thanks, Dr. Wells. Yes, we're here today for the dissertation defense and final oral examination of Kevin Orner. Just wanted to briefly introduce you all to Kevin. Most of you already, but Kevin came to us from Wisconsin. He's originally from Minnesota, but he did his undergraduate degree in civil engineering at the University of Wisconsin, and it was at the University of Wisconsin that he sort of first encountered environmental engineering as an avenue for improving people's lives. That was something that really motivated him. So he took the opportunity to come to our master's program, our Peace Corps master's program, and earn his master's degree while serving in the Peace Corps in Panama. Following graduation from USF with his master's degree, he returned north and worked in engineering practice for a couple years. But continued to be motivated by this idea of engineering research and practice as ways for having a beneficial impact on the world. So he came back to USF for his PhD. He's done work in the laboratory. He's gone back to Central America for more field work in Costa Rica, all centered around the theme of nutrient management. And so that's what we'll be hearing about today. Thanks, Kevin.
Well, thank you, everyone. It's great to see many familiar faces. This is definitely a culmination of a lot of work, and I couldn't have done it without people here. So thank you, especially to my wife, Sarah, my parents, Keith and Brenda, and many friends and family who are both in this room and also connected remotely as well. So if at any point you want to grab food or drinks, we've got food from La Teresita. There's rice, beans, plantains, chicken, and also some tea, lemonade, coffee. So feel free to grab some. I'd also like to thank many of the people here. I want to extend special thanks to my co-advisors, Dr. Cunningham and Dr. Mahelsik, my committee members, Dr. Ye, Dr. Stefanakis, Dr. Harwood, and Jeanette Brown. Many people here have also been helping me in the lab and also writing papers, so thank you. And also I'd like to acknowledge grants from the National Science Foundation, the US EPA, and from Fulbright. So just a little bit of an overview of what I'll be covering today. Chapter 1 will be the introduction, and then chapters 2 through 5 are my 4 primary research topics. So chapters 2 and 3 are about how to select for different technologies to manage nutrients. Chapter 4 is based on my laboratory work with the microbial fuel cell, and then chapter 5 was based on my work in Costa Rica looking at managing agricultural waste. And then chapter 6 will be conclusions and recommendations. So this slide is probably familiar to many of you, but my work is motivated by nutrients. And nutrients come from many different sources. And the sources that I'm primarily concerned with my research are both from centralized treatment plants and septic tanks. And also chapter 5 will look into agricultural runoff as well. And the issue is that when there's excess nutrients that end up in water bodies, it causes algae blooms. And when the algae blooms decompose, it uses up the dissolved oxygen in the water, and that prevents the flourishing of aquatic life. So we're looking at ways to minimize this excess nutrient runoff to improve aquatic life. My work is also motivated by the Sustainable Development Goals. These were developed by the United Nations, and they're in effect between 2015 and 2030. And the one that I primarily interact with is Sustainable Development Goal number 6, which is clean water in sanitation. But one of my other goals is I want to integrate not only SDG number 6, but there's also many other of these sustainable development goals that can be integrated with treating wastewater. So this includes, for example, zero hunger. If we can develop fertilizers can be used to grow food. We can also turn wastewater into a source of energy, so that leads into goal number 7. And we can also treat wastewater in effective ways to reduce greenhouse gas emissions and act for sustainable development goal number 13. And one of the primary forces of my research here is this idea of managing these nutrients, not just at the centralized treatment plant. So what I have here is we can manage nutrients here at the city scale, whether that's mainstream treatment or we have sludge treatment, and we have this nutrient-rich centrate that's often returned to the head of the plant. That's another place where we can manage nutrients. But 2 other places that we can manage nutrients as well are at the building scale. So for example, a building has a toilet. What if we source separated urine and we're able to manage nutrients at that scale? And what if we can manage nutrients, for example, at the community scale or the neighborhood scale? There's a group of houses. So I'll be looking at this concept of managing nutrients at different scales throughout my presentation. So the overall goal is to contribute to the achievement of multiple sustainable development goals through the removal and recovery of nitrogen and phosphorus from a variety of influents and also at a variety of scales. So objectives 1 and 2 are looking at different nutrient management technologies that are available at these 3 scales. Objective 2 looks at how to evaluate these different technologies, how we can choose one technology over another, and at what scale it's most appropriate. And then objective 3 is looking at how do we apply this planning matrix to a case study of Hillsborough County. Objective 4 is looking at how to use a microbial fuel cell to manage nutrients and recover energy at the side stream at a centralized wastewater treatment plant. And then finally, objective 5 is my Fulbright work, looking at how we can treat cow and pig manure using anaerobic digestion and also struvite precipitation. So first, I'll be diving into chapter 2. This is looking at reviewing the different technologies available and figuring out what nutrient management technologies are most appropriate at the different scales. And this is work that has been published previously in environmental engineering science. So here we have a house of quality, and this is basically just a way that we can look at different technologies and figure out which one is most appropriate. So here, the 2 most important parts of this figure are the technologies. So we'll list all the different technologies available here. And here, I'll get into a minute, what are some different technical characteristics that we can evaluate these technologies. And these different characteristics will also have different levels of importance. So here are the technical characteristics. There are 10 of them that we used for this study. They go from ease of operation and maintenance. These are some of the things that Jeanette was previously talking about. To be appropriate, we need to consider a lot of things, and that includes how much does it cost? Is it a mature technology? How is it impacting the environment? How is it doing in removing nitrogen and phosphorus? And also, does it look pretty? So we combine these into this house of quality matrix, and there's a lot going on here, so I want you to focus just what's on this red box here. So again, we have the different technical characteristics abbreviated here at the top, and here we have some different technologies that are available at the side stream for sludge treatment and managing the nutrients in the liquid effluent from the side stream. And these different symbols here, there are 5 different symbols. There's minus, 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 0, plus, and plus, plus. So minus, minus received a score of 1. Plus, plus received a score of 5. And we basically computed these final scores by multiplying the importance factor. For example, here 0.8. This would receive a score of 2. Multiply those together, and then sum across to get a final score. So this is looking at side stream. No treatment received a score of 32. But as you can see here, there are a few different technologies that score well above no treatment. So using this tool, we can say, hey, maybe you don't currently do anything for side stream treatment. Here's some technologies, for example, that a municipality should consider at their plant, given these different characteristics and how important it is to that particular municipality. So one technology that I'll be diving into deeper is chemical precipitation and crystallization. So you can see here with this plus, it does a great job at phosphorus removal. It doesn't do as good a job at nitrogen removal, but there's also an opportunity to couple different technologies together. So for example, in a later chapter, I'll be looking into, could we couple chemical precipitation and tie that into, for example, microbial fuel cell to remove nitrogen. So some takeaways from this chapter, the rankings at each scale generally aligned with current practice. What that meant, the building scale was simply flush toilets because they're easy to maintain. Everything gets flows down to the centralized treatment plant, and more facilities are now implementing chemical precipitation at the side stream. And another note here is that future trends will likely affect the technologies available, their different maturity levels. So as we continue to see trends of resource recovery, we not only need to remove nutrients, but also looking at recovering nutrients or energy or water. Test beds, the ability to test these different technologies to lower the risk factor for different municipalities to implement them. And also looking at the advantages of building and community scale treatment. What if, for example, there's a golf course way at the neighborhood scale that's really far from treatment plant? Does it make sense to do treatment closer to where, for example, it could be used on a golf course in the future? So moving to the next chapter, chapter 3, this was looking at the same House of Quality tool, but applying it to a case study of Hillsborough County. So I was looking at how these different nutrient management technologies at these 3 different scales would affect centralized treatment. So in order to achieve this objective, we looked at completing a mass balance for nitrogen and phosphorus, and then seeing how we could estimate these different technologies, how it would affect the different nutrient fluxes of nitrogen, phosphorus entering mainstream treatment. So this was implemented in Hillsborough County. So here on the left-hand side of the table is the number of houses for 2 communities that I looked at. One community is Henderson, the second community is Tudor Chase, which is shown here. So you can see there's some water body here, some different roads and buildings in the neighborhood here. The Henderson community only had 1 pump station, but here there are 4 pump stations. And then you can see there's also the listed flow rates entering the wastewater treatment plant and leaving the plant, and the total nitrogen and total phosphorus concentrations, both at the neighborhood scale and all the way down at the treatment plant. And a couple things I want to highlight here. I apologize for this red box. So the total nitrogen, this number is 40. This down here is only 5.5. So you can see there's a lot more total nitrogen at Tudor Chase than total phosphorus. But now we look at, for example, the side stream at the treatment plant. There's 135 milligrams per liter of total nitrogen and 170 milligrams per liter of total phosphorus. So if we're looking at the neighborhood scale, it's more concentrated of total nitrogen. But here at the side stream, there's actually more total phosphorus than total nitrogen, but the levels are more or less the same. So this can help us make decisions about where it's most appropriate to look for nutrients. So for example, if we're looking at total phosphorus, it's much more concentrated at the side stream than it is, for example, at the Tudor Chase neighborhood. So applying this, for example, here's what the House of Quality looks like. So this is using the same tool as chapter 2 and applying it to the case study of Hillsborough County. The importance factors are slightly different. These were important factors given to us by a representative from Hillsborough County. So you can see the top 2 performing technologies here are ion exchange and chemical precipitation. So here I have a slide that basically takes those 2 technologies, chemical precipitation and ion exchange, and looks at if you implemented these 2 technologies in the side stream, how would it affect the flow, how would it affect nitrogen, and how would it affect phosphorus. So both of these technologies really don't do much in terms of reducing flow, but chemical precipitation reduces total nitrogen concentrations by 20%. Ion exchange can reduce up to 95%, and total phosphorus, both technologies remove approximately 85% of total phosphorus. So we can see that has some impacts for the fluxes entering the mainstream treatment. So for example, if you have total phosphorus concentration of 170, 85%, now you only have 26 milligrams per liter now entering the mainstream. So this can have significant effects on mainstream treatment if you do this at the side stream. So this same exercise was carried out with the top scoring technologies at the building scale and the community scale. And here is a summary of some of the results. So this black dashed line here is the original loading at the mainstream in kilograms per day. So this is for nitrogen here. And you can see there's a lot more nitrogen here coming from the building scale and community scale, whereas here down in the side stream treatment, we're not seeing much nitrogen loading. So we can see, hey, if we implemented composting latrines or did source separation and applied the urine as fertilizer, and also various community scale technologies, they did a great job at being able to remove nitrogen. So these are some of the technologies we should definitely be looking at if we want to reduce nitrogen loading to the mainstream.
What's the difference between the black bars and the gray bars?
So these black bars here, these three technologies are the building scale technologies, and these gray bars here are for the community scale technologies. Thank you. So this is the same exercise, but looking at phosphorus reductions. And here we can see that just as we saw higher concentrations of phosphorus from side stream, here we can see that if we want to reduce phosphorus loading to the mainstream, these bars here are much higher. So if we do some technologies like chemical precipitation or ion exchange, this is the amount of reduction that we can see going back to mainstream. So if we look at, again, the building scale technologies in black or the community scale technologies here in gray, we can also see some removal, some reduction of phosphorus. But the big factor here is that in the side stream, this is a great way to reduce phosphorus. So some takeaways from chapter 3. Building scale source separation and community scale nutrient management could reduce nitrogen loading by over 50%, and side stream had minimal impact, but side stream did a great job at reducing phosphorus loading to the mainstream, and building scale and community scale technologies also had moderate impact as well. All right, so chapter 4, this was looking at the microbial fuel cell. This was published in the Journal of Environmental Engineering by ASCE. And this was looking at the microbial fuel cell along with the fixed film nitrification reactor, not only to obtain energy, but also reduce nitrogen using the liquid effluent of struvite precipitation. And the 3 specific objectives here are quantifying nitrogen removal, quantifying power generation, and seeing if these technologies merit further consideration. So here's just a figure of what this technology how it looked like in the process. So here we have struvite precipitation. Entering struvite precipitation, we have high loadings of both phosphorus and ammonium. Struvite precipitation removed a lot of the phosphorus, so now we have low phosphorus concentrations. We still have high concentrations of ammonium. This entered the nitrification reactor, and this converts the ammonium to either nitrite, NO2, or nitrate, NO3, and that requires an oxygen source. And that effluent of nitrite or nitrate entered the cathode. And here in the anode, we put in a carbon source, and through this process, we were able to generate CO2 along with protons and electrons. And the protons crossed the membrane. The electrons went through the circuit to the cathode. And here we have nitrite and nitrate along with the protons and the electrons. And through this reaction, we were able to convert the nitrite or the nitrate into nitrogen gas. So the key thing to take away here is that we're converting the ammonium and then the nitrite and nitrate from a liquid form to a gaseous form. And if it's in a gaseous form, it's no longer in the liquid. So overall, this process can generate energy here, and also the effluent, we also see, especially a lot of nitrogen removal. So here is what the process looked like. In the lab, we had an external nitrification reactor. The effluent was put into the cathode here, and here's the anode. So we saw some interesting things as far as nitrogen removal. We expected from the struvite reactor effluent to the nitrification effluent, we expected the total nitrogen levels to be about the same because we were simply converting the liquid form of ammonium into the liquid form of nitrite or nitrate. However, we did see this big difference here. We did see some nitrogen removal. And again, we saw some nitrogen removal here between the nitrification effluent and the cathodic effluent. So we hypothesized that there was some simultaneous nitrification, denitrification occurring because there need to be a denitrification reactor to move the nitrogen from the liquid form to the gaseous form and thus lower the total nitrogen concentration. So here are the different nitrogen species. On the left in the black is the cathodic influent, and on the right is, in the gray, is the cathodic effluent. And here we can see there were moderate levels of ammonium entering and leaving. But the big takeaway here is that we saw a lot of nitrite in the influent to the cathode and very minimal nitrite in the effluent. So this means two things, that the ammonium was being converted primarily into nitrite instead of nitrate, and that was being denitrified in this cathodic reactor. So we were able to see this big drop in total nitrogen. So some takeaways from this chapter. We observed that the primary benefit was not the ability to produce energy. We didn't see much as far as power generation, but we did see a great ability to remove the additional nitrification, which is important, especially after struvite precipitation, which is able to reduce a lot of the phosphorus, but not a lot of the nitrogen. So this is a good secondary treatment process after struvite precipitation. However, there are still many improvements that need to happen, including improvements in aeration, electrode spacing, and materials to increase power output. And this work is continued by Alen at the pilot scale, working with Hillsborough County. Next is chapter 5. This was my Fulbright work. So this was looking at nutrient fluxes of swine manure treatment system in Costa Rica. So the system consisted of an anaerobic digester, and then I built a low-cost, locally produced struvite precipitation reactor to help achieve multiple sustainable development goals. So the three specific objectives here, we're looking at a mass balance for nitrogen and phosphorus in the two digesters, building a struvite precipitation reactor, and then doing a mass balance of nitrogen and phosphorus in and out of the struvite precipitation reactor. So this is just to give you a better idea of what it looked like. On the left is one of the two tubular digesters. These were already built. You can see on the bottom, they did some excavation, and that's where this plastic tubular digester rests. And the pipe comes in here. That contains the swine manure and some cow manure, along with the water that was used to rinse the manure from the pens. And the hydraulic residence time is about 21 days. And you can see the plastic bag at the top is a storage bag for the biogas. In the middle here is myself along with 3 maintenance workers at the University of Georgia, Costa Rica, along with the reactor. I apologize for the contrast here. And then you can see here is a cloth filter bag that was used to collect the solid struvite. So the struvite was then collected on this bag while the liquid went through, and then this could be collected, stored, and then used. So this was how the reactor looked like in the field. On the far left with the red roof, that's where the cows and pigs are located. They have 2 digesters. One is located here. They just have this green fencing just to prevent any insects, rats, whatever from puncturing the two plastic containers. And then the effluent from the digesters came down here into these two storage containers for the digester effluent, and those were manually lifted in a bucket into the top of the struvite precipitation reactor, and then this effluent was brought into a series of lagoons for further treatment. So here's another figure showing the flow of the different streams. So here we have swine waste, and then twice a day cows were milked, and any time that the cows defecated while they were being milked, that runoff went here into the first digester, and then a couple of years ago, they added some more swine, so they needed to build a second digester to handle the additional loading. So that was swine waste here, goes into the second newer digester. So then I collected in the storage container these two digester effluent streams, and that was placed into the struvite reactor. So there were two different ingredients needed for the struvite precipitation reactor. So struvite is magnesium, ammonium, and phosphate, and we were able to get the ammonium and the phosphate from the digester effluent, but we still lacked magnesium. Through a series of adventures, I was able to find that local salt production facility had this byproduct called bittern, and bittern contains a lot of magnesium, and they're basically just dumping that into the Gulf. So I came down, got a bunch of storage containers. There's a waste stream for them, but it was something productive and useful for me. So that was the magnesium source. And then we also need to raise the pH. Struvite precipitation reactions happens about a pH of 8.5 to 9, and the digester effluent had a pH of about 7 or 7.5. So we need to raise the pH. So we found out that baking soda, if you heat it in an oven for about an hour at 100 degrees Celsius, it converts the baking soda into soda ash along with carbon dioxide and water. So baking soda can be bought for about $1 per pound. It could be bought locally, and this was a great source of a base to use in this reaction. So all the different sampling points of the liquids and the solids were then entered into the series of equations to basically see what was happening with the nitrogen and phosphorus entering and leaving the digester, number one, digester number two, and the struvite reactor. So just the simple takeaways here is that I have equations for phosphorus in equations 1, 4, and 7, equations for nitrogen in 2, 5, and 8, and then 2 solids balances as well. So what did we see happening with the different mass balances? We saw that there was about 25% reduction of total phosphorus in the digesters. You can see the numbers go from 27 to 18, and then from 43 to 36. And also the numbers in the parentheses are the phosphate concentrations. So as expected, the digesters were digesting the phosphorus and the nitrogen. So we saw phosphate levels increase from 4 to 11, and from here, 11 to 21. So there's a lot more loading in digester number 2 than in digester number 1. And then we also saw in the struvite reactor a decrease from 69 to 27. And the struvite reactor was a batch reactor, which means that it wasn't run continuously. So basically I took samples in the storage container, and then after I ran the struvite reaction, which was about a 50-liter batch. And these numbers are simply approximations if you decided to treat all of the day's volume instead of just the 50-liter batch that I did. So we did see about 60% of the phosphorus loading end up in the struvite, which was promising. So this is the same mass balance, but for nitrogen. So here we saw that there was a minimal nitrogen removal in the digester, so most of the nitrogen continued on into the digester effluent. So this is important that the digester is great at producing biogas, but isn't effective for nitrogen reductions. So we were able to see a little bit of reduction here. We also actually saw a little bit more total nitrogen in the effluent. We think this was either because we somehow missed a little bit of this digester influent. Maybe this was closer to 200. instead of 199, or else possibly there was some resuspension occurring. And we did see the loading of 298 in, 268 out. So this is similar to literature values for struvite precipitation, that it's really good at reducing phosphorus, but not quite as effective for reducing nitrogen. So now just looking at the solids. So if we were able to produce 100% struvite, we would see that it would be about 10% magnesium, about 6% nitrogen, and 13% phosphorus. And from the analysis that I did at the University of Costa Rica in San Jose, we will see that the solids that I produced in my struvite precipitation reaction are very close in terms of magnesium and in terms of phosphorus. So that was very promising. This number here, 2.4, is slightly less than the 100% struvite number. And we actually think that what was occurring was, in addition to the production of struvite, we actually think there was some potassium struvite forming. Thus, we will see this potassium level of 9.9 in the solid that we had, whereas you probably won't find that in 100% pure struvite. So these numbers do differ from the synthetic fertilizer that they currently use. The terminology they use is an NPK value of 10-30-10, so 10% nitrogen, 30% phosphorus, and 10% potassium. So there would be, they would need to use more of this struvite product, considering that, well, it may contain the same percentage of potassium. These numbers of percentage of nitrogen and percentage of phosphorus are a little bit less. But the benefit of struvite is that it is a slow release fertilizer, so it's less likely to be washed off, for example.
All those percentages are by mass?
By mass. So some takeaways from chapter 5, we'll see that the digesters had a phosphorus reduction of 25% and minimal nitrogen reduction. And then in the struvite precipitation reactor, we saw a reduction of 79% of phosphate and 12% of ammonium. We're also able to show that you can use low-cost, locally produced materials to not only build the reactor, but also for some of the different ingredients of bitter and soda ash. And this would help facilitate progress towards multiple sustainable development goals, not only improving sanitation, which is goal number 6, but some of these other sustainable development goals, such as food security and preserving local ecosystems. So moving on to the conclusions and recommendations, the first chapter looked at reviewing some of these nutrient management technologies, but at multiple scales, building community and city scales, and then somehow being able to decide between those different technologies. And we're able to produce this House of Quality tool that was able to integrate stakeholder priorities to recommend different technologies at each of those 3 different scales. Chapter number 3 looked at the case study of Hillsborough County, and we were able to show that for Hillsborough County, nitrogen can be most effectively managed at the building and community scales, and phosphorus can be most effectively managed at the city scale side stream. Looking at chapter number 4, we were looking at the microbial fuel cell with the laboratory study, and we saw that it was able to remove nitrogen. It produced some energy from the liquid effluent of struvite precipitation. And then in the last chapter, chapter number 5, we were able to show that agricultural waste can be treated using the tubular digester in addition to the locally produced struvite precipitation reactor. So overall, we were able to show that removing and recovering nutrients can be done not only from a variety of influence, no matter if it's at the side stream or at the mainstream building scale, but also looking at agricultural waste as well. So these are all places where nutrients occur and they all cause eutrophication, and there's lots of technologies available for all these different influence and all these different scales. So moving to the future, I recommend being able to improve interaction with stakeholders in addition to developing these easy to use models so that some of these this research that we're doing here can be easily incorporated by people who are applying these technologies. Something that USF has done well, and a lot of other places, is using test beds to easily integrate some of this research into practice. And then in addition, integrating multiple disciplines. It'd be great if we could see small businesses integrating with the business departments develop these businesses. We've got great interactions here with anthropology, looking at behavior change and how these technologies are actually being used. And I'm also interested in how we can integrate information technology, how we can handle big data to help us make decisions as well. So here's a summary of some of my scholarly contributions, some conference proceedings, oral presentations. And with that, I'd like to thank you for your attention. I'd love to answer any questions that you may have. Thank you.